Welcome back, everyone. So in this video, we're going to be talking about 3 different scenarios that can be found when talking about conservation of angular momentum. Now, before we get started, the most important thing you need to remember for all of these is for the definition of conservation of angular momentum, which says that in a closed system, which means in the absence of an outside torque, the angular momentum will stay the same. Which means as long as something's in the system, the angular momentum will stay the same. If you bring something outside the system, that could change the angular momentum. Now, the first thing we're going to talk about here is the conservation of angular momentum for a single object. Okay, this could be presented as pretty much anything. Typically, it's something like an ice skater, where the ice skater starts by spinning with their arms out, and then slowly brings their arms in. What happens then? Okay, well, let me demonstrate. Okay, so I'm going to start by spinning in my chair with my arms out. I'm going to spin about 1.5, 2 times. Then I'm going to bring my arms in. I want you to observe what happens. Okay, so let's watch this. Okay, bring my arms in now. Okay, now hopefully you noticed that as I brought my arms in, I sped up. Now, I didn't do anything to the floor to make me speed up. I just brought my arms in. Now, how does that work when talking about conservation of angular momentum? Well, let's think about this for a second. All right, let me kind of continue my drawing here. We have our ice skater, but now their arms are in, and they're moving faster. They're rotating faster. They didn't do anything for that to happen. They're just rotating faster. Now, how does that work? Well, remember back from the previous video that for conservation of angular momentum, you have I omega equals I omega. So your rotational inertia before something happens, before I bring my arms in, times the angular velocity before I bring my arms in, equals the rotational inertia and the angular velocity after I bring my arms in. Okay, now, remember that rotational inertia is that mass times r squared. Right? So in other words, with the same mass, I'm the same mass, if I have the radius of my mass distributed further away, I'm going to have a higher r, which means I'm going to have a larger I. Okay, now, by bringing my arms in, decreasing this r, what I'm doing is I'm lowering my rotational inertia. If I'm lowering my rotational inertia, in order to keep this side equal to this side, my angular velocity must increase. So I speed up. And if I were to bring my arms back out, the opposite would happen. Okay? That's how this works. That is why ice skaters, to change their speed while they're spinning, or say a ballet dancer or something like that, when they bring their arms in, they speed up faster. Okay? They're actually lowering their rotational inertia by lowering the radius at which their mass is distributed. Okay? So that is pretty much all you need to know for that one. Okay? Maybe they'll ask you, they'll say, oh, if they'll give you numbers and ask you to calculate one or the other. But the idea is, because the rotational inertia changes, the angular velocity must change as well. Now, the next one is fairly common. What you'll have is, let's see, I'm not a very good drawer, but I'm going to do my best here. Let me start that drawing over. Let's do it as a circle. All right, so you've got a circle, a disc maybe, and that disc is rotating, right? It could be a solid disc. It's rotating with some angular velocity. Okay, now, at some point, maybe you'll put a second disc on top of this originally spinning disc. So the original disc is spinning, then a second one on top of it is not spinning. Okay, then as they collide, they both spin together, right? Sometimes you'll see it with no friction. That's fine, no worries. Now, what happens here? Well, it's very, very similar to the idea of that one person bringing their arms in, changing their angular momentum, or their rotational inertia, not their angular momentum. So the idea is that's being conserved. Okay, so we have our I times omega equals I times omega. Remember, your I is your mr squared. Okay, now, typically in a problem like this, the two disks are identical. So you're not changing the r at all, but you are changing the m. So by adding this extra mass, you're increasing your rotational inertia. In order to keep this side equal to this side, your angular velocity must drop. Okay, so this side would be before you drop that second disk onto the first. This side would be after. Lower rotational inertia, higher angular speed. After you drop the disk, higher rotational inertia, lower rotational speed. Now, a lot of times for this particular problem, they'll then ask you to compare the rotational or the angular momentum on both sides, but also the rotational kinetic energy. Okay, very simple. If the whole system ends up slowing down, the rotational kinetic energy of that first rotating disk will decrease, and the second disk that was not rotating, now it is rotating, the rotational kinetic energy for that disk will increase. Okay, it acts as an inelastic collision, which means that the kinetic energy of the whole system changes as well. Right, so that's just kind of another way to look at that. Now, the last bit that we'll see, very common, is, let's say you have a rod that's fixed at one end. So this is the rod, it's fixed at one end, it's allowed to rotate along that rod, or along that fixed point, okay? Now, what you've got is, it could be a stone, could be a lump of clay, it depends on how the question is being asked. Sometimes you'll see the same scenario if it were a lump of clay and a disc that's just rotating. Not really a big deal because the key piece is going to be the same. Now, that stone or lump of clay is going to be moving towards the rod at some point. Okay? Question might ask, what is the angular momentum of the system after the collision compared to the angular momentum of the system before the collision? Well, what we're going to do here is take this whole thing. We're going to take the rod and the stone or the lump of clay, whatever this thing is, and say that is the system. By putting both things into the system, we can say it's a closed system, which means the angular momentum of the system remains the same even after the collision. So even though this thing isn't rotating to start, the angular momentum remains the same. Now, you might be wondering, hold on a second, this is moving linearly. How can we say the angular momentum is the same if this is moving linearly? Well, remember, we have a way to say, hey, our angular momentum equals the mass of this linearly moving object times the linear velocity of that object times that radius, where the radius is simply just how far away the object is from the pivot point. Okay, L, I don't know if you can see it, L equals m times v times r. So that is a way we can say that this object moving linearly has an angular momentum. Okay, all three of these problems are kind of, for lack of a better term, pivoted on the idea that in a closed system, the angular momentum stays the same. All three of these systems are a closed system. You have the one person, that's the system. You have those two disks, both disks are part of the system. You have something like this, both the lump of clay or rock or whatever this object is, and the rod, or if this were a disk, that's all part of the system. Okay, you've got to take both things as part of the system. That way you can say the momentum before equals the momentum after. Okay, when it comes to angular momentum, right, we're not going to expect you to do much in the way of mathematics. Maybe for the ice skater one, you'll have an rotational inertia before and rotational inertia after, and maybe one angular velocity, and then you have to find the other one or some other kind of unknown, right? But to kind of put the bow on top of this video is to say, try to take as many objects in the system as possible. Because if you take all those objects in the same system and say there's no outside torques involved, then the angular momentum is conserved for that system. Okay? Well, that's all we got for that one. See you next time.